What do dams, reservoir gates, and water tanks all have in common? They often use curved surfaces to hold back massive amounts of water. But how do engineers calculate the immense forces these surfaces must withstand? The math for flat surfaces is straightforward, but for curves, it gets tricky. The pressure force is always perpendicular to the surface, which means its direction is constantly changing along a curve. So how do we find the single resultant force? The secret isn't a complex integration. It's a clever free body diagram trick.
In order to analyze the hydrostatic forces on a curved surface, this gets a bit more complicated since now you don't have just the surface like a tank or a wall or a dam in which you will have these hydrostatic forces acting vertically or horizontally. You have a much more complex shape in order to integrate. And an easier way to do this is by separating the forces or the resultant force on its vertical and its horizontal components. You can see this graphically as here we have a tank with a curved surface, and here you would take this as the resultant forces. You have the hydrostatic forces on the horizontal on the horizontal cut, but on a vertical direction of Fy, which would be distributed evenly. And on here, the vertical part of the cut, we have the distribution of forces that as they go down, they increase. But essentially, what we see is that for any given resultant force, you have the resultant force and you have the component Fh and Fb. Fh would be equals to the respective f of x. Fx or the horizontal force, hydrostatic force that would eventually need to cancel out each other. And for f of vertical, you have f of y and weight, which is the weight of the fluid. For f of r, or the magnitude of f of r, you have to get the Pythagorean theorem of f of h and f of b, which is square root of f of h squared plus f of b squared.
So this is an example that we can do for this topic, which would be this cylinder that has a 5 meter length and then a 0.8 meter radius. And they ask us to respond the hydrostatic forces acting on the cylinder and the weight of the cylinder per meter length of the cylinder. So what we can do is first of all assume that the friction is negligible and the atmospheric pressure acts on both sides. Then we can get our free diagram which which tells us to get the vertical and horizontal force doing these two equations, we would give us 36.1 and 39.2. And then the last thing that we would get would be the weight, which by doing this equation would give us that it's 1.3. Now, both.
So the net vertical force from the fluid on the surface Fb is equal to 37.9 kilonewtons acting upward. The two components Fh and Fb are shown as vectors, and they are combined tip to tail to form the resultant force Fr. The magnitude and the angle are calculated on screen. So we have that Fr is equal to the square root of 36.1 squared plus 37.9 squared is equal to 52.3 kilonewtons. Then we take the arcotangent of 37.9 over 36.1, which is equal to the theta angle 46.4 degrees. We have that the total force is equal to 52.3 kilonewtons of gate length acting at 46.4 degrees from the horizontal. And because it's a circular surface, we know this force must pass directly through the center of the circle.
Now for the part B of the problem, we need to find the cylinder's weight, and we know that the gate is just about to open, which this means that the cylinder will be in equilibrium, and the only forces acting are Fr and the weight. With this, we can make a sum of moments, which is Fr times the radius times the sine of theta, which is this one, minus the weight, since it's going down, times r. By doing this, the r cancels out, and plugging in the different values, we can get that the cylinder's weight is 37.9. We can see that this number is exactly the same as the vertical forces that were calculated earlier. And this is because this is how the gravity control mechanism works.
So to summarize everything we have seen in this video, we learned about how the hydrostatic forces act upon a curved wall specifically, because we have learned about how they act on a triangular wall or a vertical wall. But today we learned a three-step process that you can consistently use, as you can see in my notebook. First, you have to imagine the fluid block. And here we're using the example from the previous slide. You compute the vertical force and the horizontal force. And using this, you can find the angle and the resulting force, the angle obviously of the resulting force. And this is extremely useful because, as my colleague Medellín mentioned also in his example, you can find the ratio, for example, in the hydrostatic forces and how they were lifting the cylinder up. And you could find the ratio between the force and the weight that was in that cylinder. And it can also be really useful in examples like a submarine, a dam, and a water tank, and even in a diver's helmet. But thank you very much for your attention, and we'll see you in class. Bye.